Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. It's been a while, but seems like most of you guys found your way back. Okay, so it's been 2 weeks or a little bit more since we last met. So lots to catch up on. Well, not really, but just so you guys know, prior to today, you should have been up to lecture 19. By the end of today, you should be up to lecture 22. You do have a quiz next week on things between the test, on topics between the test and lecture 22. So I just want to make sure you guys know that. But yeah, so you have 3 lectures to watch today. So let's actually get on with it. Let me share my screen. And let me make sure that I can see the chat and all that good stuff. Okay, all right. So, you know, students always ask, so I thought I'd share what's going on. So this is what the class average currently looks like. The top one is the class average before the test, right, which was pretty good. We were pretty skewed to the right. We had like almost half the class with an A. Right now, we have about a third of the class with an A after the first test. I actually had a couple people did not take the test, and yeah, I'm not sure if one or both of those people have dropped. I looked into this last week, but I don't remember. There's been a lot of changes over the past few weeks. But yeah, so now before the test, the class average was a B plus. Now after the test, it's a B minus. These are both good. So as an instructor, there are 2 levels at which I care about the class. I care about all of you guys individually. I also do care about how the class is doing on average. So sometimes I step back and I look at, if the entire class was one person, how is this person doing? And this person is doing pretty okay. Of course, C average or better is good, and we are currently at a B minus, so we're doing better than good. That being said, you know, it did start skewing more to the left after the test, but I guess that's to be expected. The test was the test is probably the hardest thing you guys have done. That being said, I don't really think things will get much harder. So if you survived up to this point, I think you can pretty much end the semester where you are now or better. So I anticipate that the class average is going to stay around a B minus, or maybe even get a little bit better if some of the students who haven't been as serious as they should have been decide to start getting serious. That is, I wouldn't be surprised. So what we've done up until the test, we did a lot of the calculation type stuff that you should know. So like how to compute a derivative, how to compute a limit, how to write the hard math stuff. Now for the rest of the class, you're going to be focusing on applying all of that. So it's like now you're just going to be doing that. You're doing the same things. You're just now going to be doing those things to solve word problems and that sort of thing. And when it comes to those problems, there are strategies and things of that sort and sequences of steps that we take. And I'll, of course, go through those with you in class. And when it comes down to it, the actual computation part is actually going to be a little bit easier. So overall, if you pay attention, you keep up with it, start being a little more serious than you were, things should be fine. Things should end up like this or better after the final. If it comes down to it, so this last histogram here was for the test itself. So this was for test 1. Like I said, 2 people didn't take the test, so there's zeros here like that you won't see, but yeah, was a 70 average, which was about a C average for the test, which is okay. The most someone got was 108. So we actually had someone get over 100. Yeah. So that was just for curiosity's sake. But let's actually jump into the test so that you guys can get to your lectures. Okay, so what I'm going to do for today, the plan is to just run through the test, pretty much do it with you, let you see what the answers should look like, why those guys are the answers. If you have any questions, you can stop me and ask. And of course, afterwards, if you have any general questions, I can take those as well. So let's get into it. So this is the first question. Below is the graph of a quadratic function in blue, right? The segment of the tangent line to f is drawn when f is 2, right? So a segment of the tangent line. What is f prime of 2? Okay, so this was something that didn't really require any calculus calculations. It actually requires calculations, minimal calculations that you would have known how to do since a long time ago. So basically, this is just testing whether you understand what it is the tangent line is actually doing, and what does it mean to be f prime at 2. So if you know what a tangent line is, it is the tangent line that has the slope being equal to the derivative, and it touches the curve at the point of interest. So pretty much f prime of 2 is just asking about what is the slope of f at 2, and to figure out the slope of f at 2, we can just figure out the slope of the tangent line. So yeah, all we have to do is find the slope of this red line, which is, rise over run. So it rises by 4 units, and the run, it looks like is, so here we see that 2 squares gives us 1. So this is 1, 2. So it's 4 divided by 2. And that's that one. So that was the first question. Find the slope of the red line. This one was just also testing your knowledge of slope. So it was, again, sort of a concept question. You had to do very minor calculations for this. And it basically asks you to put these numbers in order. So again, if you understand what it means to be a derivative, you understand that it's talking about slopes. Basically, what this is talking about is ordering the slopes at every point. We know that when things go down as you move from left to right, the slope is negative. If you go up as you move from left to right, the slope is positive. And if you're kind of flat and leveled off, the slope is 0. So we kind of know that, and you're just going to, hopefully you know that, and now your challenge is just to put these guys in order. So it should be, we want to order these from smallest to largest. So I would start by figuring out who's obviously the largest, who's obviously the smallest. You'll notice that there's only one point along a part of the curve that is moving up. So that part has positive slope. Pretty much everyone else has negative slope or 0. So D has positive slope. So that's the largest for sure. You'll notice that C is at a point where it's kind of flat and leveled off. So C has slope 0, and that would be the second largest. So D and C would be 5. Write that over here. And 4. Okay, so far, so good. Now the others for A, B, and E, these guys are all negative slopes. So now I just want to know who's the most negative versus the least negative. And of course, most negative, the guy that has the largest magnitude and is negative, is the guy that is the steepest. You can see here that E is the steepest. And the A and the B segments are actually straight line segments. And you can see here the A is actually steeper than the B. So when it comes to the smallest slope, E is going to be the smallest. A would be the second smallest, and B would be the third smallest. So it'll be 1, 2, 3. And those would be the numbers that you type in here. Okay, so that again, no calculations, really just a concept question. And that's kind of the concept. That's what kind of should go through your head. as you're doing this problem. This one here does ask you to show your work. So this is one of the problems where you had to like actually do the calculations and write it out and justify the answer. So let's actually do that. So we know the average rate of change formula, or hopefully by the test you knew the average rate of change formula. This guy was average rate of change. That is just going to be f of b minus f of a over b minus a, essentially, right? Where your a is the first endpoint and your b is the last endpoint, the endpoint on the left and right respectively. So yeah, so this is just going to be f of 3 minus f of 1 over 3 minus 1. And at this point, it's just a matter of you plugging into the function f of 3. It's f of x is 1 over x squared. So f of 3 is 1 over 3 squared minus f of 1, 1 over 1 squared, all over 3 minus 1, which is 2. So this is just 1 over 9 minus 1 over 2. I can think of the 1 as 9 over 9. So 1 over 9 minus 9 over 9, that gives us minus 8 over 9 over 2. And of course, dividing by 2 just means I'm multiplying the denominator of the top by 2. So this is keep, change, flip. I can cancel 2 into the 8. And so I get minus 4 over 9. Right, so that's the average rate of change here. So now I can go up. So it should be minus 4 over 9. That is not here. It's actually none of the above. But of course, to get full credit for this, you have to show minus 4 over 9 as the answer in your work, right? So yeah, was none of the above for this one. Okay. Any questions so far? Are we okay with everything I've said so far? All right. Well, Joe's giving me the thumbs up, so I think we're good. Daniel's also like, okay, Porter. All right, thanks. All right, so we're gonna solve the following equations. Okay, so we had a couple parts to this one. Yeah, let's make sure we know how to solve these equations. So we have e to the 3 minus 2x equals 4. And what we learned is that logarithms and exponentials functions are inverse functions of each other. So if we want to get rid of an exponential, which in this case we do because we want what's in the power of the exponential, so we'd want to get rid of the exponential, you can use logarithms to get rid of the exponential. So what I would do is I would log both sides. ln would be the nicest logarithm to use. In fact, in general, in a calculus context, ln is probably the best log to use, regardless of the base that you have. What would happen here is that would cancel based on our log rules. And so on this side, I would have 3 minus 2x. On that side, I would have ln 4. And now it's just a matter of solving for x. So I need to isolate this guy. I can move him to this side and then subtract the ln 4. And so now my x is going to be 3 minus ln 4 all over 2. And that looks like the option here. Option B, the second option. Here's just an equation that you want to solve with logarithms, just to make sure that you know how to manipulate logarithms as well. So there are several approaches that could work with this one, but I would probably go with the approach that says, let's first combine all the logarithms on the left. So we have the log of something plus the log of something else. That is actually the log of the product of the things based on the log rules. Okay, so that gives me, this is the log of x squared plus x minus 2, it looks like. And now we have that rule that says, when we have log to the base something, log to the base a of b equals c, it means that a raised to the c equals b. You can also think of this as just putting both sides in the power of 10, raising both sides to the 10. By language, that doesn't make sense. But when I said that, I explained in class that sentence, you kind of know what it means. Okay, so you can either use the definition of the logarithm or use that thing where you put 10 as the big base and you put each side of this equation into the power of 10. But either way, you would get x squared plus x minus 2 equals 10. Then we would have x squared plus x. This is just a quadratic equation, so we know how to solve that. We're going to bring everything to one side. Then try to factor, because that would be the best case scenario. It looks like 4 and 3 should work with a positive 4 and a negative 3. So x is equal to minus 4 or x is equal to 3. Now, of course, we do have to make sure that we check these in the original. X is minus 4 definitely does not work. Makes log negative. Right, so remember that we can't take logs of negative numbers. Well, you can, but not in this class, right? You'd get a complex number. So here you have log of x minus 1. So if I plug in x equals minus 4, that's a problem, right? Because I would have log of negative something. If I plug in x equals 3, here I would have log 5. Here I would have log 2. Those combine into log 10, and the log of 10 is 1. Because here, remember, when we don't write the base of the logarithm, in this class, we assume it's log to the base 10. That's not true in all contexts, but in our context, that is. So it turns out here, x equals 3 checks. So you do have to go and make sure that it works in the original. And so this leaves us with choice A. Another one, this has 3 parts. This is another concept question, so not a lot of calculations to go along with this one. So this is kind of going back to when we were talking about limits and what does it mean for a limit to exist, what it means for something to be continuous, etc. So we're only looking at this graph between on the interval -2 to 8. And we just want to know where are the points where the limit does not exist. This basically means that you're looking for the points where the left, as you're approaching from the left and you're approaching from the right, these guys don't agree. It turns out that this happens everywhere except when x is -1. So there's actually only one point for which the limit does not exist. This is when x equals -1. The limit coming from the left is 1, while the limit coming from the right is -1. Everywhere else, the limit exists. If I had put less than or equal to 8, 8 would also be an answer, but we're strictly less than 8. So we never actually get to the edge here. So we're always a little bit to the left of 8. So we're always approaching it from the right and the left and getting the same thing. We'll be on that circle either way. Let's move to this. Now, continuity has a very intuitive definition when you're looking at a picture. Of course, there's a technical definition with limits, but you can use the picture definition. Basically, it's the part of the graph that you can draw without lifting your pencil off the page. We say we're continuous there. Obviously, at x equals -1, we have to lift up our pencil off the page because we have to make that jump. The next time we have to lift up our pencil off the page is when x equals 2. Here we have to write a hole and we have to jump somewhere to fill in the point. So there are two situations here where we have a break or a disruption in the function. It doesn't just continuously go on. So we do have 2 points where we're not continuous. So we're not continuous when x is -1 and when x is 2. Go back up and make sure that that's it. Yeah. Yes. Okay, let's look at the third one. Where does the derivative not exist? So remember in class we mentioned the derivative doesn't exist in 3 main cases. So this is when we are not continuous, when we have sharp corners, and when we have vertical tangent lines. So those are the situations you want to look for. So not continuous, so obviously there's going to be at x equals -1, and 2, the guys that we got from the continuity part, those guys are also there. But now we might have additional things. So now you'll realize that at this point, there's a sharp corner. And at this point is a vertical tangent line. Literally the line that's going through 6 that you can see is vertical and it's tangent to the function. So in total, we have 4 points where the derivative does not exist. So this is when x equals -1, x equals 2, x equals 4, and x equals 6. Limits. Okay. Now we're getting to the fun stuff. Okay, compute the following limits. So limits, we spent a while on limits, couple classes, maybe 3, I don't remember, 2 or 3. But we do know that the main strategy for limits, whenever you're faced with a random limits one, the first things you want to try to do is to plug in. So this is going to be the go-to method for most of those situations. The only time that plug-in method doesn't work is if your function is very weird and complicated and it's like piecewise and stuff like that, and then you have to plug into different branches and you might get something right. So that's the situation that can arise. But for the most part, as long as you can actually plug in and the function is continuous around where you're plugging in actually works. And at this point, you would know about the continuity requirement. If this function is continuous at the point, then you can find the limit by plugging in. And this function is continuous at the point. In fact, this function is continuous at all points. The only possible issues is when the denominator is 0, but x squared plus 1 is never 0. So we'd actually just plug in. Plug in. So I'm going to just plug in -1 for x. So that leaves me with 2 in the denominator. In the numerator, it leaves me with 2 minus 1 plus 2. So that's 3 over 2, it looks like. That's none of the above, but this is one of the problems where you have to show your work. So to get full credit, you had to show that you got 3/2. So yeah, that one was just a plug-in. This one. So here you're noticing that as x gets close to 3, what's going on to this guy? You notice that you can't actually plug in because you're not continuous at 3. If I plug in x equals 3, the denominator will become ln of 1, which is 0. So plugging in x equals 3 would make the denominator 0, no bueno. Okay, so what I do realize now is that I want to know what the numerator is approaching. So this here is approaching. So the denominator is 0, which is already bad, right? And however, my strategy will depend on what the numerator is approaching. So let's actually see what the numerator is approaching. When I plug in x equals 3 in the numerator, I would get e to the 3 minus 3. That's e to the 0, which is 1. 1 minus 1 is 0. So in the numerator, I have 0. So this means I actually have a technique that can deal with this situation, L'Hopital's rule. So this means I can say by L'Hopital's rule, and that's how we write it. This is equal to the limit. Provided the limit exists, it's actually going to be the same as this. I'm going to take the derivative of the top, which now at this point, we should know how to find that derivative, which is that divided by the derivative of the bottom, which is 1 over x minus 2. So in other words, this is just the limit as x approaches 3 from the right of minus x minus 2 e to the 3 minus x. At this point, I can plug in x equals 3, and there are no issues. When x equals 3, x minus 2 just gives me 1. So the coefficient there is 1, and then I get e to the 0. So I get minus 1. Okay, here's another one. We have a ratio of polynomials and we're taking a limit at infinity. So we do know the strategy for this one. Basically, you focus on the highest powers. So in the numerator, the highest power is a minus x squared. And in the denominator, the highest power is a 3x cubed. The highest power is in the denominator. Therefore, the limit actually approaches 0. So that's just based on a strategy. This is what we call bottom heavy. And as I mentioned in class, you can literally write out the phrase bottom heavy, and I will accept that as showing work. There's a little bit more complicated mathematical reason for why we can make this conclusion. I went through it in class, but then I'm like, okay, it's just kind of silly to write this out. We all know where it's going. So just write bottom heavy, and that's like showing your work. Okay, moving on to the fourth limit. Okay, so we're not going off to infinity, so we need to be careful here. We're actually approaching 3. And as you can see, when you plug in 3 into the denominator, you actually get 0. If you plug in 3 into the numerator, you also get 0. So you could use L'Hopital's rule here. But these are two nice polynomials. My knee-jerk reaction is actually to factor. So I would do these guys factor. Would have to be 3 and 1. Minus 3 plus 1 should work. In the top, maybe 3 and 2. Minus 3 plus 2 should work. The 3's would cancel. This is actually going to be just now the limit as x approaches 3 of x plus 2 over x plus 1. This function is actually continuous, you can just plug in 3. So it's 5 over 4. Also, if I call this L, since L approaches 0 over 0, L'Hopital's is also an option. So you might have done that. So you could have gotten that L was, according to L'Hopital's rule, the limit as x approaches 3. If you take the derivative of the top, which is 2x minus 1 divided by the derivative of the bottom, which is 2x minus 2. And at this point, you can plug in 3. So that's 6 minus 1 on top, which is 5, and 6 minus 2 on the bottom, which is 4. So either way, you can get 5 or 4. A couple ways you could have done that one. My knee-jerk reaction would have been to do the factoring, but if you saw that L'Hopital's rule applied, that's also fine. Right, all that is running through my mind because I know about the strategy of finding limits. So, I can simplifying would be the second thing I would think about before thinking about any special techniques. So, all right. So here's one that asks us to use the definition of the derivative to compute the derivative. So this is referring to the limit definition. No credit was given for any other method. So yes, I knew at this point you could find the derivative with a shortcut. You could rewrite the square root of x as x to the 1/2 and do the power rule, and you can immediately see that the answer would be minus 1 over 2 radical x. Okay, so the answer should be B, and you should actually know that from the very beginning. It's just now I want to make sure that you could get there by using the definition of the derivative. So let's actually work that out. So here we have our, remember our f prime is the limit as h approaches 0 of f of x plus h minus f of x over h. Now our f of x is 2 minus radical x. So this first part would look like 2 minus the square root of x plus h minus parentheses 2 minus the square root of x. So that would be the first step. You would notice here that the 2's actually cancel, 2 minus 2. And then I would have minus a minus radical x. So there's a positive radical x that comes out. And then I have that minus radical x plus h. So now I want to figure out a way to actually cancel the h. That is the point. So we need to simplify. Rationalizing the numerator seems like the thing that makes sense here. So I would multiply by the conjugate. Multiply and divide by the conjugate. So now in the top, remember the conjugate just makes it looks like difference of two squares. So it's going to be the square of the first term minus the square of the second term. Parentheses are important. If you forgot the parentheses, chances are you're going to get it wrong. So now we have something that looks like this. And right, so here we would end up with minus h in the top. Because the x would cancel the x. And now the h's cancel. So ultimately, I look like the limit as h approaches 0 of minus 1 over radical x plus radical of x plus h. And then I just plug in h equals 0. So that's what it would look like for you to write that down. And of course, that's option B. Okay, so this is the second part. It asks us to find the equation of the tangent line. So from part A, we know that the derivative is minus blah, blah, blah. So here, we know that for the tangent line, so we know that m is going to be the derivative evaluated at 9. So this is going to be minus 1 over 2 radical 9, because it was 1 over 2 rad x. So this is minus 1 over 6. We also know that when x equals 9, our y value would be 2 minus radical x. So it's 2 minus rad 9. So that's 2 minus 3 or minus 1. So I know that my m is minus a sixth, and I know that my coordinate point x1, y1 is 9 comma minus 1. So now it's just a matter of y minus y1 equals mx minus x1. So that's the tangent line. It looks almost like A, but not quite. Everyone else is expanded, so let's expand. So if I take 9 times 1/6, I get 3 over 2. So my y would be minus x over 6 plus 3 over 2 minus 1. Minus 1 is 2 over 2. So this is 3 over 2 minus 2 over 2. I would just get 1 over 2. Is that an option? Yes. Here. Okay. And this brings us to the last set of problems on the test. Just checking, do you know how to find derivatives? And as I mentioned, moving forward, you're not even going to have to find derivatives of things that are as complicated as this, but I do want to make sure that you know the rules. So just checking that, do you know how to, look at a function, know when you should be using the chain rule, the product rule, the quotient rule, all that good stuff, how to actually dissect functions in your head. Do you know all the basic derivative rules to apply, et cetera, et cetera, et cetera. So that's what this problem is trying to test. So yeah, in all of these parts, I believe I gave you 4 parts. Find the derivative, find y prime, which is specified here as dy dx. So I'm thinking of x as my independent variable. At this point, it wasn't that important to actually know that idea to make sure, okay, I'm thinking of x as my independent variable. It kind of felt natural based on the forms that I gave you, but later on, it's actually going to make a difference, right? So especially when you're doing like related rates and things of that sort, where your independent variable is not x in general, it's going to be t in general, or maybe something else. In general, right, your independent variable doesn't have to be x, right? But here it's just for emphasis. All right, so if my y is equal to ln of x plus 1 raised to the 2. Here, I would use the chain rule. So I differentiate the outer function, which is just bringing the power down, multiply by the derivative of the inner function, which technically is u prime over u. So here I use the chain rule. And in here was the u prime over u. Yeah, that's pretty much it. I think, yeah, so that's actually this choice right here. Not bad, like one step. So that's that one, chain rule, one step. Okay, here my y was 5x plus 2 over 6x plus 3. So probably the most straightforward way to do it, the way that most people would have done it, would be the quotient rule, right? So I think of this as, you know, f over g, which means that my y prime is going to be look like f prime g minus f g prime over g squared. And so that's what I'm going to do. So it's going to be the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. Okay, so simplifying this a little bit, multiplying out, that's 30x plus 15 minus 30x minus 12. And so that's just 3 over 6x plus 3 squared. Doesn't seem to match. Let's make sure that we can write this properly. What we can do is notice that the denominator here is a 2x plus 1. And here there's a common 3. So I can actually factor out a common 3. And get that 2x plus 1. And so when that comes out, that will be 3 squared. And so this cancels that. And so essentially I have 1 over 3 times 2x plus 1 squared. It's option B. There's another problem. And I'm assuming we're still good. Everyone okay over there? Still alive? Are we understanding so far? Any questions on what I'm doing so far? Okay. All right. Well, Daniel's still alive, and so is Joe. Okay. All right. Let's keep moving. So this one here, I would probably just rewrite it with the half power to begin with, and then do a chain rule. So here, rewrite, and here do chain rule. At this point, we can actually clean things up. the 2 is going to cancel into both of these 2's because I can factor out a common 2. And so this looks like x plus 1 times x squared is 2x to the minus a half. Which is, it's actually the first option. If I wrote this, this is actually x plus 1 over x squared plus 2x to the 1/2. It's like option A. Five parts. Okay, so here we have, give me a second here. So here we have what? Change back to green. Y equals e to the x cubed plus x to the x cubed. Now we have a rule for the first one. We know that the derivative of e to anything is e to the u. The derivative of e to the u is u prime e to the u. So the first part is no problem. However, the second part, we don't really have a rule for that, strictly speaking. This was the topic of where we learned to integrate, differentiate something like that, is log differentiation, and actually gave you a variation on log differentiation that I like to use when I want to rewrite something on the spot. And that's just rewriting it as an exponential so that I can use the exponential rule that I already had memorized. So that's how I would go about this. But you could actually split this into two separate problems and do log differentiation on the second part. But I'm going to just rewrite on the spot. So I can write this as e to the ln of that thing. Or in other words, that's e to the x cubed ln x using the log rules. Okay, so here I just rewrote. Because I know that e to the ln of something is equal to the something, as long as the thing is in the domain of the logarithm. And then I can rewrite the top because I know ln of something to a power is that power times ln of the something. So I can rewrite and using both of those rules. And at this point, I can now just differentiate using my derivative rules. Take the derivative of the power times the original function. Here, take the derivative of the power times the original function. So differentiate using the fact that I know the derivative of e to something is u prime e to the u. So what is the derivative of the power? So in the power now, we have x cubed times ln x. I would use the product rule. So I would differentiate the x cubed, leave the ln. Now I would leave the x cubed, differentiate the ln. So that's the product rule there. So this is just 3x squared e to the x cubed plus, in here I would have 3x squared ln x plus x squared. And this I can write as x to the x cubed. So I just rewrote this guy here. back to original form. And that's actually the answer. Does that look like anything? That looks like the last one. Well, the one before the none of the above. So there we go. So that one was complicated if you didn't remember that you can do that little trick, or that you had to use like log differentiation or something like that. But that was something that we spoke about in class. When the base and the power has variables, you can't just apply the power rule or something like that. It doesn't work. Last one. So we have to do implicit differentiation for this because our x's and y's are mixed together. This is implicit differentiation. And this is partly why I emphasize what I meant by the derivative earlier on, y prime equals dy dx, because you do need to know who's the independent variable for implicit differentiation. And basically the idea is you go through and you differentiate as usual, except if you differentiate anyone who is not the independent variable, then you have to multiply by their derivative with respect to the independent variable. And that is a consequence of the chain rule. So yeah, if we have x squared minus 4xy plus y squared, what I'm going to do is I'm going to just go through and differentiate everybody according to the derivative rules. So it looks like here I won't need anything more sophisticated than the power rule and the product rule. But I just need to remember, if I differentiate anything that's not an x, I have to multiply by the prime of that thing, essentially. Here I'm differentiating x squared. We know that it's 2x. I differentiate an x, don't do anything, moving on. I'm going to do the product rule here. I'm thinking of minus 4x as one function and y as the second function. So if I differentiate the first function, I just get minus 4, leave the second, plus leave the first function, minus 4x, times the derivative of the second. Derivative of y is y prime, plus 2y is the derivative of that according to the power rule. However, I have to multiply by y prime because it's not the independent variable. Derivative of 4 is 0. So we have that. So now this part here was because of the product rule. And now what we want is we want to isolate the y prime. So I'm going to move everyone who does not have a y prime to the other side. So here I have minus 4xy prime plus 2y prime. So move over the 4y and the 2x. Then I'm going to factor out the common term and divide. So 4y minus 2x over 2y minus 4x, that can be reduced. And it looks like the answers were reduced. So let's actually reduce that. There's a common 2 in the top. So I can take this as 2y minus x over y minus 2x. Looks like the third option. Okay. And essentially that was the test. I believe that was all non-bonus problems, and I can run through the bonus problems with you. But hopefully, even especially after I went through it with you guys, hopefully it didn't seem too bad. You had an hour and a half, and we went through that in less than an hour, with me explaining everything that I was thinking. So, I mean, I could go through the bonus as well. I mean, we have time. So let's actually just do that. So this is something that you would have learned about after the test. So that's where the bonus credit comes in. So this is just for people who could actually manage to get ahead. The main thing here, the linear approximation formula, is the following. So it's f of x is approximately equal to f of a plus f prime of a times x minus a when x is near a. And in general, you want to interpret x's, I mean, I say this just to make it stick out in the minds of students, but it's not really the ugly value. All numbers are beautiful, but this is the ugly value we want to figure out f of x for, right? So it's an ugly value and we don't really know what the function is doing at this value. We want to actually approximate that. But what we do is we pick a nice value that's super close to that value, for which we know, I know what the function is doing at that value, and I know what the derivative is doing at that value, right? Which Heisenberg might have something to say about that. But for us in Calc 1, that's doable. So yeah, so that's essentially the thing. And there's a whole lecture where I'm going through this. I don't know if you watched it already, probably have at this point. So that's what we're going to do. We want to approximate the square root of 8, of 8.8, right? Which is not a nice value. It's not something you'd know off the top of your head, square root of 8.8. So want to approximate square root of 8.8. So what you do is you first define the function that looks like the thing you want to approximate. Define f of x to be the square root of x. Of course, I want to know what this does when x equals 8.8, which is an ugly value that I don't know the answer off the top of my head. However, of course, I'm going to need to find f prime because that's in the formula. Now we will take our x to be 8.8. That's the ugly value that I want to figure out. And a would be something that's super close to that value that I already know all the answers for because it's a very nice value. So that would be 9. That's super close to 8.8. And it's a value that I know what the square root and what 1/2 radical x would look like. So this would mean that my f of a is just f of 9, which is just square root of 9, which is 3. And I would also know that my f prime of a, this is just f prime of 9. This will be 1/2 rad 9. This will be 1/6. So this would mean that my square root of 8.8, this is approximately equal to f of a plus f prime of a times x minus a. Well, that's just going to be 3 plus 1/6 times 8.8 minus 9. So this is 3 plus 1/6 times minus 0.2. So that is 3 plus 1/6 times 0.2 is 2/10, which is 1/5. So that ends up being 1 over 30, and 3 I can think of as 90 over 30. Something like 89 over 30. And so that's option B. And of course, you'd have to use this method to show, right? So it says no credit for any other method because you can just plug into your calculator and know what the answer is, but we do want you to approximate it with this. That was linear approximation, which is a topic that we would have done after the test. This last problem is regarding exponential growth and decay, which is another topic that we would have done. I believe at this point you would have seen this in the lectures already. P of t is the size of a population of bacteria. It doubles in size every 15 minutes when t is measured in minutes. An initial sample of this population had 10 individuals. Assuming exponential growth, what is the size of the sample after 40 minutes? You may leave your answer in exponential form. Okay, so let's actually do that. So we do know an equation for doubling time. That would be in the handout that I would have given you guys, which is on the class webpage and all that stuff. So we do know that doubling time equals ln2 over r. And so this means we know it doubles every 15 minutes. So this means 15 is equal to ln2 over r, which means that your r is equal to ln2 over 15. So we know the PERT formula, P of t is equal to P naught e to the RT, where P naught is your initial value, which we're told is 10. Now we know the R is ln2 over 15 times t. So that is measuring the size of the population at time t. We want the size after 40 minutes. So this means size after 40 minutes. Well, that's just P of 40. So it's going to be 10 e to the ln2 over 15 times 40. And I probably reduced that. So let's see. We can reduce that. 5 into 15 goes 3 times, 5 into that goes 8 times. So this would reduce into something like e to the 8 ln2 all over 3. And that looks like the third option. Okay, so that's the entire test, including the bonus problems, which at this point, you probably know how to do the bonus problems, but you didn't necessarily have to know the bonus problems on the last one. I think that's everything. Hopefully that wasn't too bad. You kind of see how we did everything there. But yeah, that's it. Any questions on anything I did or anything else moving forward? So as I mentioned today, you should 7.2. 7.2, hold on. Oh, the L'Hopital's rule problem? So go back over 7.2. So there, 7.2 is really something talking about something called L'Hopital's rule. So that was one of the special techniques that we did in class. It basically says, suppose we have limit as x approaches a of f of x divided by g of x, and this approaches 0 over 0 or infinity over infinity, plus or minus. So you have a limit of a ratio, and either the top and bottom both go to 0 or the top and bottom both get infinite. Then if this limit exists, it is the same as you can take the derivative of the top and the derivative of the bottom. So that was something called L'Hopital's rule. Basically, if you're looking at a limit and both the top and bottom are going to 0 or both the top and bottom are getting infinite, you have the option of doing something like L'Hopital's rule, in which you differentiate the top and differentiate the bottom, and that will give you the same answer, provided the answer actually exists. And there's nothing that says L'Hopital's rule has to be applied once. You can apply it several times. Sometimes you have problems where that's what you have to do. Sometimes you differentiate the top and bottom and you still get a 0 over 0. You can go again, and you can go again, and you can go again. And the moment you stop getting one of those and you evaluate the answer, then provided it exists, meaning you get a number, a value for the limit, then the value that you do after this process will always be the same as the value that you would have gotten after of doing the original limit. So that's what we kind of did here. So I realized that if I plug in x equals 3, which is my knee-jerk reaction because of the limit rules, when I have limit of x approaching a, one of the things I try to do immediately is plug in a, right? Because that's one of the basic strategies. However, if I plug in x equals 3, I get e to the 3 minus 3, which is e to the 0, which is 1. Then if I take 1 minus 1, that gives me 0. So the numerator gives me 0. If I look in the denominator, if I plug in 3, I get ln of 3 minus 2, which is ln of 1. Ln of 1 is also 0. So I'm in the 0 over 0 case, which puts me within the L'Hopital's rule territory, because I have the 0 over 0. So what I do now is I just differentiate the top and the bottom, right? So the derivative of this is u prime e to the u prime here is minus 1. So it's just minus 1 times the original function. The derivative of the minus 1 is 0. And so that's the derivative of the top. Derivative of the bottom is u prime over u. U prime here is 1. The denominator is x minus 2. So that's just 1 over x minus 2. Then I keep change flip. So I can multiply by the x minus 2. And at this point, I plug in the 3 and everything is fine. There's no division by 0 going on, no strange behavior. That's just a straight up, this function here is continuous at 3. I can just plug that in. Plug that in and I get 1 as the answer, minus 1, because there was the negative from this part. Is that clear? I mean, this is the rule I was using. This is what I was taking advantage of. Okay. Yeah, so there were some special techniques I gave you guys for limits. The thing with ratio of polynomials and the top heavy, bottom heavy, or the highest powers are the same was one of the special techniques. L'Hopital's rule was another. Any other questions before we move on? So remember, you're scheduled to get through 3 lectures today. So 20, 21, and 22, or get at least up to 22 by the end of today. So you can start practicing for next week's quiz, which covers everything between the test and that. So make sure you check the syllabus on the class webpage so you know what topics are covered in the quiz and etc. But if there are no more questions, we will end there. Okay. All right. Well, thank you for your attention. We'll wrap up there. Of course, if you have any trouble after getting through lecture 22, you can email me and we'll try to set up something if possible. But for now, we'll get there. You guys still have a lot more work to do for this class. So I'll let you guys get to it. But we will stop there for now. Hopefully you guys understood everything and that test wasn't bad. Overall, the class isn't doing so bad. It's at a B- average right now, so we're pretty okay. And like I said, if you stay as serious or get a little bit more serious, I don't see that getting actually worse. I think if you are good up to this point, the rest of the class should be okay. Not saying the rest of the class is easy, but if you understood everything coming up to this point, finishing off should be pretty okay. Like you're not going to do anything harder. So that being said, we'll stop right there. I'll let you guys get to the lectures and yeah, let me know if you have any issues, but we'll stop right there. So have a good day. Yes, if you want to look at your current grade in the class, Jupyter grades, I believe it's up to date at this point. So log into Jupyter grades for that. Yeah, and you should see a bunch of emails to me from Jupyter grades. So once you go into the link, there should be some item in the left menu bar that said something like, "Oh, check your report card" or something like that. Okay, all right. That being said, have a good day, everyone. Good luck with your studies, and I will see you guys in the next one.